Hi everyone, welcome back to our second part. It's my great honor to introduce you our next speaker, Professor Gagandeep Singh. He comes from UIUC and his research focus on the intersection between artificial intelligence and the programming language. Let's welcome.
Thank you for the introduction. Okay, so we will continue what Matthew started, but now we will look at more specialized methods um, for neural network verification. So first, Matthew has presented box analysis, which is an incomplete method. Now I will start with uh, one of the complete method based on mixed integer linear programming. Now, when I present these kind of works, the first question is why not use SMT solvers, because they can handle general functions, and they haven't actually been applied. What we have observed so far is that they are not as effective as something like mixed integer linear programming. Now, we for sure don't know why that is the case, but one conjecture is that they are not specialized for the particular computations that you see in neural networks. So the implementation itself is lacking the heuristics to handle the kind of nonlinearities or the pattern of nonlinearities that we actually encounter in neural network verification. You can actually transform the neural network verification problem into an optimization problem, and these MIL-based solvers are actually more specialized for handling this, and the way we encode it allows us to leverage all the different heuristics that these solvers have been using. So in practice, what we have seen is that using these kind of MILP solvers is more precise than using SMT-based methods. So we talk about complete verification. It is not always possible because the general problem is undecidable. If I gave you an arbitrary neural network with arbitrary activations, I mean, the deep learning practitioners are usually very creative, so they regularly design all kinds of weird activations, right? So if I were to design any weird activations, the problem can be easily made undecidable. So if you are going for arbitrary networks and arbitrary properties, you cannot actually do complete verification. But we will look at a very specific case, which Matthew already introduced, where you can actually do complete verification. Even then, the problem is NP complete, uh, and therefore it lacks scalability. It can scale up to networks containing a few thousand neurons, but once you start getting into millions, unfortunately, it does not work. Okay, so let's look at the property that Matthew was mentioning, which was robustness to L infinity perturbations of fully connected networks with ReLU activations. Okay, so how does a usual mixed integer linear programming problem look like? It's similar to linear programming in the sense you have a linear objective function, you have set of linear constraints between neurons or variables here in the second box, and you can provide bounds on the variables. The only difference is that some of the variables can be integer, so they only take discrete values. Most of the variables are continuous, but some variables can be integer, and this integer part differentiates it from the linear programming, and it also makes it harder to solve. So usually there are like state-of-the-art solvers. So when we do neural network verification, we exploit these solvers, but people have actually also developed specialized solvers for neural network verification. Okay, so to encode a neural network, you can use mixed integer linear programming. Now we are looking at a fully connected network with ReLU activation, so it has very limited types of computations going on. So you only need to handle 4 different kinds of computations. You have to encode the affine layer and the ReLU layer, and you have to encode the precondition and the postcondition in the fragment that I just described. So I want to keep this interactive. If you have any questions, you can ask me. Okay, so encoding an affine layer is straightforward because it just applies a linear transformation on your input. So if your input is x, what the affine layer does, it multiplies the vector x with weights and adds a constant bias term to get your output, and this can be easily encoded as a linear equality constraint. The interesting part is, and you will see when we design all these other verification methods, is actually in handling nonlinear computations. So the setting of neural network is a bit different than usually when you do program verification, is because you have lot of nonlinear transformations going on. So usually when you write programs, I have not seen any program that actually applies 1 million nonlinear transformations on program. Like you usually write like statements, sparse statements like y is equal to x1 plus x2. You don't write like y is equal to x1 plus x2 plus x million, right? So you have like in neural network setting very different kind of computations going on. You have different kinds of affine transformations, and you have a lot of nonlinear behavior. But the set of computations that you handle is bit restricted than handling programs. If you're handling like usually neural networks, fully connected, etc., you don't have to reason about loops, recursive function, and so on. So that is, I would say that overall the problem is incomparable with program analysis in the sense that you have very different kind of challenges. And you will also see because of that, some of the classical approaches for program analysis do not work as effective in the case of neural network verification. So we have to design specialized techniques, and also the techniques that we develop for neural networks are not going to work as well for programs. Okay, so let's look at just the encoding. You don't have to look at all the details. Somebody came up with it. What this just implies, and you will see that when the network is positive, the input x is positive, the output is equal to the input, and when it's zero, when it's negative, then the output is zero. Now, what you see is that here for each ReLU statement, you have to include a integer variable which only takes 0 or 1 values, right? So each ReLU in this encoding is going to correspond to an integer variable, and that will introduce branches in the when you actually try to solve it, and because of that, there is less scalability of these solvers, right? So here in this encoding, it assumes that you have available L and U bounds on neurons. If you don't know what are the bounds from beforehand, you just say it's between minus infinity to plus infinity. But we will leverage the box analysis that Matthew introduced to have these box bounds available. Yeah. 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 So actually, if you can prove that the lower bound is positive, then you don't need to consider branches because you know it will only be positive. So there is some pre-processing that we do to compute this L and U fast with incomplete methods. So the more precise it is, you can actually eliminate a lot of branches. So there are two false improvements here, and we will see the combination later, is that it improves the scalability of the solver because the search area is reduced, and then it also can be used to improve the precision of incomplete method, and we will see that combination later. Then you have to encode the precondition as a mixed integer linear program. In this case, it's just an L infinity ball which just induces interval constraints on all the input variables. So what you will say is that all the inputs xi prime are between xi minus epsilon. Xi is the original image, and xi plus epsilon. Similarly, you can encode the post condition here. If it is that O0 should be greater than O1, you would try to say, you would make an objective function that the minimum value of the difference between O0 and O1 is positive. If it is positive, then you know for all the inputs in your input set, the property holds. Now, if you're going to do multi-class verification, you would have to prove it for all the classes, right? So you would say that O1, O2, O3, O4 to O9 or O100 are going to satisfy this property. So far clear? So if the objective value is more than 0, you have proved the property. If not, you can get the point where it is less than 0, and that would be the concrete counter example for your verification. Okay, let's look at the mapping. The generic MILP problem was asking to maximize or minimize an linear objective function. In this case, this would be just the difference between the two output variables. For in terms of linear constraints, you would just plug in the constraints from the affine layer and the ReLU MILP encoding, and then you would provide bounds for each variable in the network. You can compute this bounds by box analysis or other kinds of analysis that I will just introduce. And then for each ReLU, you would have integer variable. Okay, so this is what Matthew had showed. The bounds that he presented were correct. He was just missing the biases over the neurons 0.5 and -1. So this is the results that we saw in the previous analysis, and we could see that the property cannot be verified with box. And now we will see how we can verify the same thing with mixed integer linear programming, right? So from the network, we have extracted all the affine transformations. So x3 was equal to x1 plus x2, and O0 was equal to x5 plus x6 plus 0.5. And here in this encoding, you also provide the precondition, which says what are the values x1 and x2 can take. And then you also add these constraints for the values x5 and x6. And in the encoding, you introduce the integer variables a5 and a6. And you can also use the box bounds that you got from this analysis for specifying the range of values that all the intermediate neurons in the network can take. If you don't have these bounds available, you would just say -infinity to +infinity. The solver will figure out what should be the bounds. Okay, so let's see how these box bounds will help to solve or boost the scalability of mixed integer linear programming. Okay, so how this will work, the goal here is not to go into all the details of how the mixed integer linear programming solver will be working, because it employs a lot of heuristics. We use Kurobi, which is a commercial solver, has many things going around. We don't know what they're doing, but I just want to give an overall high level idea of how the verification method will work. So it's usually based on branch and bound methods, right? So what happens here is that you have in the encoding two integer variables a5 and a6 that can take two values each. So you have 4 integer cases, right, corresponding to a5 and a6, and for each integer case you can solve a linear program. So in the brute force case, you would consider 4 different linear program instances, and then you will try to prove for all those 4 LP problems O0 minus O1 the minimum value is greater than 0, right? So let's look at this approach. So first, let's say a5 is 0, and that case corresponds in our encoding to the case when the input x3 is less than or equal to 0. So if you plug a5 is equal to 0 in our encoding for x5, we get that x5 is should be greater than x3. It should also be less than x3 minus 0.1. Now you can see that these two set of constraints contradict each other. So what that means is that this case is not feasible, right? So this branch you don't need to take because you have already proven that it is infeasible with your box bounds. Also, if you look at the box bounds here, which says that x3 is always positive, so you already can prove that a5 is equal to 0 is a case which you don't need to consider. So plugging in this box bounds actually helps us to eliminate some of the branches which we can prove infeasible by doing a cheap pre-analysis, right? In practice, actually, when we do this encoding, we will figure out that, okay, this variable is positive, so we will actually not introduce any integer variables in this case. But what you see here is that it has reduced the number of branches. So the number of cases that you needed to consider were 4. Now you would only consider 2 cases, which would correspond to when A5 is equal to 1, right? So the encoding has become a bit more scalable. So you only need to consider 2 cases. For A6, it's 0 or 1. So when you do A6 is equal to 0, that corresponds to the case that x4 is less than 0. If you plug in these bounds, what it implies is that x4 is taking negative values and x6 is equal to 0. You want to prove O0 minus O1. So you can take the linear constraints for O0 and O1 and subtract them, and you would get 2x6 minus x5 plus 1.5. Now you know from the case that x6 is equal to 0. So the only thing you get is 1.5 minus x5. What is the minimum value of, if you want to compute the minimum value of O0 minus O1, you would plug in the maximum value of x5, which in this case is 1.3. If you do that, you get that the minimum value is 0.2. Because it is positive, for this case, we have proven that the property holds. Now we have to look at the second remaining case. In this case, x6 is equal to x4, and x4 is positive. You do the same thing again, you get 2x6 minus x5 plus 1.5. Now x6 is equal to x4, x5 is equal to x3. You plug in the bounds, you again get 0.2. So what you see is that the box analysis was losing precision because it did not track the relational information between the neurons, but now the MILP can track this information and actually can prove the property that could not be proven before, right? So this is one of the method that we have been using for complete verification. Scales reasonably well. Okay, so this kind of is a big overview of the kind of primitive techniques that you can come up with for complete and incomplete verification. Now we will look at more specialized cases for verifying neural networks that we have been designing in the last 2-3 years. Okay, so for this, to actually illustrate our ideas, I would need a more tailor-made networks that I have handcrafted to show the benefits of the different methods, right? Here, somebody has decided that if my output x9 exceeds 3, the world will collapse or the sun may burn out, right? So I want to really prove that when my inputs x1 and x2 are between -1 to 1, the output should not exceed 3. And that's what I want to prove. This neural network has 2 affine transformations at these layers, computing x3, x4, and x7, x8, and you have 2 ReLU layers, which are given on the edges. Okay, so let's try to what we try to do in general to actually exploit the kind of abstractions that we have been using for program analysis. So the common abstract domains or abstractions that people use are known in the literature are something like box, we already saw, imprecise, scalable, but cannot prove much properties. Then there is, I would say, custom abstraction that is very useful for programs. It's called octagon domain. We actually tried to use it, but in practice, for the neural network we tried, it was more expensive than box, but it gives the same results as box, so not very useful. The polyhedra domain is a popular domain, and it can actually encode any kind of linear relationship between programs and between variables, and it's one of the most precise abstractions out there. And we had actually done previous work on speeding up polyhedra analysis for programs by exploiting custom insights, but those insights don't work in the case of neural networks. So ideally, you would like to use polyhedra, but it's very expensive. It's actually more expensive than MILP solver in practice, at least standard implementations. They are less scalable. Then people have actually used zonotopes which have proven to be particularly more effective than any of these octagon, polyhedra, or box, is because the zonotope in general are not very useful for program analysis because they lack some convergence guarantees. So if you're going for like analyzing programs with loops, etc., it's not guaranteed. Even people do widening, etc., it's not guaranteed that it would actually converge. But in the case of neural networks, you don't have to worry about convergence, at least for the common architectures. So you can use zonotope. The nice property about zonotope is that they can capture affine transformations exactly and very cheap compared with the polyhedra. And then we have actually been designing custom zonotope approximations for ReLU. Works somewhat good in practice, but 3 years ago, like box analysis in this case can actually prove only that x9 is 0 to 5, so it's not very useful. And therefore, 3 years ago at POPL, we designed a custom abstraction for neural networks. It's quite popular these days. It has been applied for a variety of neural networks, LSTMs, RNNs, of course, residual, fully connected, and so on. Uh, and what this abstraction does, it's a very custom form of polyhedra. So the restriction over polyhedra here is that polyhedra can have infinite number of constraints in general. So it can support any kind of linear relationship between neurons in the network. So to gain scalability, we restrict the number of constraints in the domain. So what we do is that each neuron in a network will only have 2 interval constraints, the upper and the lower bound, and 2 polyhedral bounds, right? So besides capturing the interval relationship, will also capture and take care of the relational constraints. So this makes the deep poly handle the affine transformations exactly. Now the octagon domain cannot handle the affine transformation exactly because it restricts the number of variables in a constraint equal to, it should not be more than 2, right? So it cannot handle the kind of affine transformations we see. And then we have custom approximations for the nonlinear activations in the network, like sigmoid, tanh, ReLU, and max pool. In terms of scalability, just to give an overview, the ReLU transformations with polyhedra has exponential complexity in the number of dimensions and the number of constraints, while with deep poly, you can do it in constant time. No question so far? Okay, always it's a indicator that everybody is either following or not following. So there's no gray area. Yeah. But the neurons in general can have more linear relationships between them, and we cannot express it in. So the restriction is that there cannot be more than 2 constraints per neuron. So you cannot have 3 constraints related with a particular neuron. I would give an example next. Where is the restriction coming for? And I will also show why this restriction enables scalability that if I allowed more constraints would not. So let's go through the analysis one by one. So you would start with the box constraints for x1 and x2. It would just add the same thing as before. Now, the affine transformation here compared to box will also keep track of the bounds for each neuron. So the affine transformation is x is equal to x1 plus x2. So you would add lower and upper bounds relational constraints that you get from the affine transformation. Now comes the interesting part, and I must say that like the last 3-4 years, people have been obsessed with how to approximate this ReLU, and people have done all kinds of things. And I would just give an example of the creativity of the field, what kind of approximations people have been doing. So the exact transformations is exact ReLU is like a piecewise linear function. Whenever I review these papers, I'm sick of seeing this figure, but you have to see it again and again. So you would draw this figure, which is the piecewise linear function. And whenever you want to like approximate it, you need to make sure that in your approximation, these green points are always included. So box, it would just create a rectangle, right? Now for some time, the triangle approximation, uh, like most papers you see in this field are actually having this figure for sure. It was considered like the best linear or convex approximation that you can do. I will show later in the talk that this was not the case, so we came up with more precise approximations. But to answer your question, this cannot be expressed in the deep poly because here you have two lower bounds. It says that xj is greater than 0 and xj is also greater than xi. So because it has two lower bounds, it cannot be expressed in the deep poly. So you can only have one of these. That is the restriction for scalability, and I will show why that is needed. So zonotope is like a center symmetric polyhedron, so it cannot also encode the triangle exactly. So what we did is we designed some custom approximations uh, for zonotope. Uh, it's in terms of precision, in machine learning community, they say that zonotope is more precise than box. It's not the case. It's incomparable. And we have actually seen sometimes that box gives more precise results than zonotope. So in terms of deep poly, because we can only have one lower bound, we keep one of these, right? And then dynamically, we select the one which has the lowest area. And you can compute the area by doing some high school math. It's a simple formula. So overall, what we do is we, for the ReLU, have these two shapes, and then we keep the one with the lowest area. It's a heuristic. There is no optimality guarantee. It then becomes like an art how to actually come up with these approximations. So you can also adapt the same. Yeah. Yeah. Yeah, you will see.
So how do you trade off those things, or is that kind of like how you settled on this kind of approximate triangle?
That's a very good question. Uh, we did experimentally, and the thing is that you want to minimize the area, right? That's the heuristic, and these are the two extreme cases. So for any inputs, the minimum area would be at either this or that. Now, actually, we have found in practice that you can use suboptimal choices. For each neuron, you don't compute the one with the best area, and overall, it has less volume for the whole layer because it maybe captures more relationship, and doing that can give more precise results. Actually, what people have done is to tune the lower bounds based upon the kind of verification property you are verifying. So you can say that your output, the minimization function, difference between O0 minus O1, is a function of the slope of these lower bounds, right? So whatever you will get would be a function of these lambdas, and then you can optimize what are the lambdas that give the best results. So people have done some gradient descent, and then actually that boosts the precision somewhat. Okay, so let's select, in our case, both have the same area. So let's say we select this approximation. So that will add the two bounds. You don't have to look at what are the constraints, but what you see is compared to the box analysis, you also add these linear constraints for x5 and x6. And because it just involves one addition and multiplication, it can be done in constant time, and it can be done independently for each neuron, and therefore it can actually be parallelized on a GPU. Now comes the most expensive part of the analysis. So notice here, the area itself depends upon these bounds L and U you get from the analysis. So what you want is that any neuron that is input to ReLU to have as precise lower and upper bounds as possible, because if lower and upper bounds are very approximate, your approximation will also be more approximate. So after every affine transformation, we want to keep the bounds of neurons to be very precise. So how do you compute after the affine transformation the bounds for the neurons? in this case x7, right? So you do affine transformation again, you can in a straightforward manner add the linear bounds, but next you have to compute the bounds of x7. What is a straightforward way to compute this? It would just be that you can just plug in the bounds, interval bounds for x5, right? So if you do that, you would get that the upper bound is equal to 5. Is that the best we can do? Not much. You can actually do better, right? So what you want, we have a specialized method to compute these bounds that are for the neurons that are input to a ReLU as precise as possible, but also very fast. And that is called back substitution. And how does it work? Now, what you can do if you're trying to compute this, because x7 is defined in terms of x5 and x6, you can use the constraints for x5 and x6 and plug in this formula. If you do that, you would get constraints defined for x7 in terms of x3 and x4. And that's where the design choice of using only one lower bound comes into play, or one upper bound. Because if you had multiple bounds, you would have multiple candidates that you can substitute here. Right? Like for each variable you are trying to substitute, x5 and x6, you would have two choices. That would result in exponential number of choices. To reduce that choice, we keep only one upper and lower bound. Okay, so you can keep doing it, and then you can get the constraints for x7 defined in terms of x1 and x2, and then you can plug in the bounds for x7 for x1 and x2, and then you get that the upper bound is more precise than 4. Overall, what this back substitution does, it computes an approximate answer to the LP defined here, which is trying to compute the maximum and minimum bounds for x7 depending upon the deep poly constraints over the other neurons in the network. But it is approximate. It gives an approximate answer to the LP. In practice, it is actually very close to the answer that you get from LP. Okay, so if you do that, you get 4, which is more precise. And then it can be done for each neuron back substitution. It can be done independently because it just requires reading constraints from the previous layer. And because of that, it can again be parallelized on the GPU. Then you can also use it for training and so on. The complexity for one back substitution is quadratic in terms of the width of the neurons, like the number of neurons in a layer, and linear in terms of the number of layers in the network. So if you can keep continuing this analysis, in the end, you would be able to say that x9 is the upper bound is equal to 4. Now, this is not enough to prevent the collapse of this universe, because what I wanted to prove was that it should be equal not more than 3. So we have got better results than 5, but it's not enough. It's still equal to 4. So then the next work that we had was at ICLR 2019, where we tried to combine abstract interpretation with mixed integer linear programming. I already showed an example where you can use the results of box analysis to improve the scalability of your methods. Now, the idea here was to use mixed integer linear programming to improve the verification precision, right? As I mentioned, the ReLU approximation is the only place in the analysis where the deep poly analysis loses precision. And the approximation error depends upon how precise are your interval bounds that are input to the ReLU. So what you can do is you can use mixed integer linear programming to compute more precise bounds for the inputs compared to what you get with back substitution. So here, what you will do is you will encode the whole network as a mixed integer linear program again, but you would also add the interval bounds that you get from the deep poly analysis to reduce the search area for the solver, and then ask the solver, give me the maximum value of x7, because this is where you were losing precision before. So if you do that, the solver is able to say that the maximum value is equal to 3. And what you see here is that once you reduce the bounds of the input, the area which kind of measures the amount of over approximation that you introduce reduces, right? So the smaller your upper bound, the more precise is your approximation. So if you actually do this refined analysis, you are able to prevent collapse by proving that the upper bound is not more than 3. Now, this kind of refinement works for shallower networks. So you can do this kind of refinement for, let's say, first 2, 3, or 4 layers of the network. But as you go deeper into the network and you want to do this kind of refinement, it does not scale, right? So then what people try to do is they try to define with the triangle. As you can remember, that triangle is more precise than deep poly. So one approach is that you can encode some of the neurons in the network with a triangle approximation, and then instead of doing MILP, you do an LP, which is more scalable, and then try to refine. Unfortunately, in practice, what we have also observed is that this does not yield much benefits over just doing the vanilla deep poly analysis. So in this case, what you did is you replaced all these max constraints for the MILP with the triangle constraints, and then you don't get any benefits. So there came like point where it was getting saturated, right? So there's only that much you can refine with a MILP solver, and only that much you can refine with triangle, right? So is there anything in between that is more precise than triangle, but is more scalable than MILP, that you can actually use for refinement? Because the approximation error actually grows sometimes exponentially with every layer. So if you go in very deep layers, you're not able to prove too much. You have to do some refinement, but it seems that the refinement also has its limits. So that was actually proposed as some kind of convex barrier to neural network verification. And then they said that not much can be done. And then we actually came up with method that broke that barrier. But before going there, let's look at what does the triangle approximation does. So triangle approximation is optimal for a single ReLU. So if you are looking at ReLUs independently in the layer, then it is the best you can do. You cannot do more precise than this. But the thing is that this approximation, it is only looking at a single neuron, and then it's ignoring the relationships between the neurons in a layer. And because it ignores these relationships, it is less precise. So it is optimal for a single neuron, but if you want to compute the approximation for the whole layer, in the whole layer there are dependencies between neurons. And because of that, for the layer-wise case, it is not the optimal approximation. So if you were to visualize this, what does the triangle approximation take? The triangle approximation treats each ReLU separately. So in this case, x3 and x4, it will consider only the box constraints them. So the input will look like a square in this case, and then you apply the two ReLUs transformations for x5 and x6 separately, and in what you get, if you visualize it in the x5 and x6 output plane, is a pentagon, right? This is less precise because, as I mentioned, you are ignoring the relationship. So it's very well known in the program analysis community that if you define transformation for a single statement and then you compose it, it's less precise than if you were to compute a single transformer for a group of statements, right? It actually makes things complicated, but of course, if you can just derive one approximation for a group of statements, it's going to be more precise than computing approximation for each statement separately and composing them together. So this is what we did. What we do is we compute approximation for a set of ReLU statements together, one approximation for multiple ReLUs together. And This is what we had at NeurIPS 2 years ago. It's called a K-ReLU framework. K-ReLU means K here is the number of ReLUs you consider together when you are trying to compute the approximation. Are there any questions? Not yet. So here, instead of only looking at the box constraints for X3 and X4, we also look at the relational constraints between X3 and X4. So the input to our framework already is more precise than what you get in the case of triangle. So what you see here is that the triangle approximation itself, it looks at X5 and X6 separately. So it can never create any constraint that relates X5, X3, and X4 together explicitly, because it has no idea what are the constraints between X6 and X4 when it is trying to create constraints for X5. In the case of K-ReLU, we actually compute these approximations directly in the X5, X6, X3, and X4 plane, the 4-dimensional plane. And because of that, we are actually able to capture the relationships that the triangle can never discover, because it's living in a space where X5 and X6 and X4 don't exist. So how do we compute the approximations, the K-ReLU approximations? In this case, 2 ReLU approximations for the neurons X5 and X6 together. So what we do, the 2 ReLUs will induce 4 paths. In the first path, X3 and X4 are negative, and X5 and X6 are 0. So we will take this input set S, and we will intersect it with the constraints generated by the first path, where these are negative. Then again, we will take the input set X and intersect it with the second path, where X3 is negative and X4 is positive, and so on with the 4 paths, right? So 4 paths, you get 4 sets computed by this intersection. Now this intersection is exact, because if you have polyhedral shape and you intersect them, the intersection is exact. The next thing you need to do is you need to, for your computing the output, you need to combine these 4 sets together. So the most precise set you can get is computed by computing the convex hull of these 4 sets. This convex hull is again a bottleneck operation. It's expensive. It does not scale very well to high dimensions. So we are not, in this case, able to do more than 3 ReLU statements together, because we use out of the box algorithms for computing this convex hull. And it does not scale as well, but up to 3 ReLU, it still gave us some kind of precision boost. So in our case, if we were to compute this convex hull, we do get a constraint that relates X5, X3, X4, and X6 together. Diagrammatically, if you were to visualize this output in the X6, X4 plane, X5, X6 plane, it looks like a triangle, which is more precise than the pentagon that the triangle was giving. Okay, so coming back to our example, instead of MILP encoding or the triangle encoding, now we will plug in the constraints that we get from our K-ReLU. So in this case, it will have these extra constraints between X5, X6, X3, and X4. And as you can imagine, the example has been tailored such that these constraints are useful. So in our case, we get that the maximum value is equal to 3. So we get the same result as the MILP, but faster. And you do this refined analysis, you are actually able to prove your property that X9 should not be more than 3. So far, so good. Now, as I mentioned, with this K-ReLU thing, it only applied in this case for ReLUs. So you cannot do it for sigmoid tanh. And it was also not scalable in the sense that you can only do a limited number of 3 ReLU statements, right? Because, yeah. Yeah, so when we did this first paper, the heuristic that we used was that to reduce the approximation error, you would like to include the neurons that are expected to be less precise in the same group. So we look at the volume of the area of the triangle approximation and sort the neurons by the area, and then we group the ones which have the highest area together. But it's not the best. It's I mean, it depends on the verification problem, and it also depends upon the neural networks. Okay, so then the latest work, which actually is state of the art currently and would be presented on Thursday at 11:35, Salon 1, is Prima, where we extended this method, the KRELU framework, to also be applicable for sigmoid 10H and arbitrary activations. And here, what we did was we developed specialized convex hull algorithms, right? So one thing with KRELU is that 3ReLU, when we compute it, the convex hull can still give, like, for relating 6 variables, it can give like 300, 400 constraints for each group, right? Now imagine if you have hundreds of these 3ReLUs going around, the solver can choke because it has just too many constraints to handle. So what are the properties we have done here is that we have a convex hull algorithm which is faster, but almost gives the same volume, but with fewer constraints. So the benefits are twofold. The solver gets fewer constraints to work with, but the fewer constraints describe the convex hull as precisely as if you did the normal convex hull. The benefits of this approach, because the approximate convex hull is faster, you can actually keep more groups together. So previously, when we were computing 3ReLUs, we looked at the disjoint set. So we partition, if you had, let's say, 48 neurons, 16 groups, where each group has 3 neurons together. In this case, we can actually compute overlapping number of groups. So if I have in a layer 48 neurons, I can actually compute 48 choose 2 or 48 choose 3 number of 3ReLU groups. We have found that having this kind of dense overlap between the groups gives more precise results than just having heuristics of choosing which neurons to group together and so on. I will not go into the more details. One more thing is that you can actually compute the optimal convex relaxation. How you do it, you would do the same thing as I said before, but you would have to do it for, it would be n ReLU. So you would intersect it with 2 to the power of n sets, and then compute the convex hull over very large dimensional polyhedra. Now, the interesting thing here is that if you compute the convex approximation, the best convex approximation of the ReLU network, and you do LP, it is complete. So it will give you the same results as a mixed integer linear programming instance. Now, why do people don't use it in practice is because the best convex approximation just has exponential number of constraints. Because of that, the solver does not work. So mixed integer linear programming actually has this branch and bound, but then it needs to consider fewer constraints. It's more scalable. So there is a trade-off between the number of constraints that the solver generates and how fast it is. What you would like is to generate as few number of constraints as possible, but they should be as precise also. Okay, so we have a framework based for neural network verification, ERAN. It is one of the most general framework and easy to use. Beyond images, we have also seen it being used by people outside computer science. So I actually saw some work where some biologists were using this framework for computing or certifying the neural networks they were using for stream water predictions. So currently, we can handle precondition which are based upon changes to pixel intensity, geometric transformation, or box regions in general around the inputs. And in terms of post condition, we can handle robustness, safety, stability. We can handle fully connected convolutional, residual, and LSTM networks. And we provide a variety of options in terms of tuning your precision. You can use box, Zonotope, Deep Poly. GPU Poly is the GPU implementation, so it has very custom GPU CUDA implementation done from scratch for exploiting performance opportunities on a GPU. Then we have the combination of abstract interpretation with MILP, combination with KReLU, and then the prima that would be described in 3 days, which combines MILP with approximate KReLU and deep poly. The good thing is that once you don't use solver, so you use only deep poly, GPU poly, zonotope, the analysis is sound with respect to the standard C semantics. So the results contain all the results you can get in by considering different rounding modes and different orders of computations. This guarantee is not available from other solvers, which do not take into account the floating point behavior. They assume that everything is done in real arithmetic, and it has actually been shown that those verification guarantees can be broken by designing specialized inputs where the floating point behavior violates the real world property that they assume. So in terms of results, you can get proved, unknown, or a counterexample if you use solver-based methods. Now I will show results on some smaller benchmarks. So usually when I present these kind of things, people first, like, depending upon the audience, they say, hey, like neural network verification, like it sounds hard, how much can you scale? And then they try to sometimes mislead by saying that the size of the network affects how much you can prove. It's not the case. It actually is a very complicated function, the verification cost of how the network is trained and what is the exact property you are trying to verify and what is the analysis you are using. So I will show you cases where very large network, which you expect should be very hard to handle, can actually be verified very fast. So here, let's look at a simpler case, medium benchmarks. So we have 1,000 test images here. So for all the 1,000 images, we have defined L infinity ball around them of certain radius. We have two networks. One is an MNIST fully connected network that has 1,000 neurons, and a CFAR10 convolutional network on the right, which has 62,000 neurons. And the two networks have been trained differently. So on the left-hand side, the network is normally trained to maximize standard test accuracy. On the right-hand side, the network has been trained to be robust with an empirical defense. What that means is that you create counter examples during training, add it to the training data set, and train again. So these networks are supposed to be harder to attack. What you see there is that once you train a network to be robust to attack, the standard accuracy drops. Here, the accuracy of the CFAR10 network is only 63%, which for a practical purpose is not very useful. So on the left-hand side, the epsilon is bigger. On the right-hand side, the epsilon is smaller. And here I compare the precision and the runtime of two methods, deep poly and prima. So deep poly just does not use any solver, and prima tries to define it with mixed integer linear programming and also the KReLU transformations, KReLU approximations. So what you see on the left-hand side, prima is able to prove 624, while deep poly only proves 259. So this is a big gap if you do like the incomplete methods. But the runtime suffers because prima takes for a single L infinity ball 6.5 minutes, while deep poly can only run in 0.9 seconds. On the right hand side, what you see is that prima again improves precision, but not so much. And that is consistent because when you train the network to be robust, the approximate methods like deep poly box are already quite precise. So using solvers does not change the precision too much, right? What you see also, the runtime of prima on this 62,000 neuron network is less than the one on 1,000 neuron network, which is 395. Let's look at larger benchmarks. Here on the left hand, both are CFAR10 networks. Left hand side, we have ResNet 18, 500,000 neurons, 18 layers. Right hand side, we have ResNet 34, 34 layers, 1 million neurons. The left hand side network is trained with empirical defense again to reduce the number of examples that you can create. And the right hand side is trained with diffai that Matthew introduced to make the network easier to verify. Now what you see is that the left-hand side network has 82% accuracy, while the right-hand side has been regularized so much to improve its certification that the accuracy is 35%, which for an practical purpose is not very useful. What you see also on the left-hand side that the epsilon is 0.002. On the right-hand side, the epsilon is much bigger, 0.03. Now here we are comparing Crown IBP, which is one of the state-of-the-art methods that scales to larger networks, and GPU Poly, which is the GPU version of Deep Poly, because the CPU implementation does not scale here. So we again compare how much can we verify. In this case, Crown IBP verifies nothing, while the GPU Poly is able to verify 648 of these instances. The runtime of GPU Poly is 6.5 minutes. If you look at ResNet 34, 1 million neurons, the runtime of GPU Poly is in few milliseconds, right? So that's what I wanted to mention, is that there's no point of just saying that, hey, I give you ResNet 100 and your verification will not scale. I can choose, depending upon the property and how it is trained, it can be that verifying your ResNet 100 is easier than verifying some fully connected network, right? So what you would ideally like is to get a network that gets maybe 80, 90% or 95% standard accuracy, but is as easy to verify as this ResNet 34, right? So here, what you see is that even if you do like the Crown IBP, which does not prove anything on ResNet 18, you can actually prove a lot with this imprecise method if you train the network to be robust. So that is a grand challenge in general for all this method, how to get networks that are accurate and robust at the same time. And you can actually prove them to be robust as well. We also have results with Prima for beyond MNIST and CFAR10 for autonomous driving, which is something we always show, but we never gave examples before. So it was unfortunate. Like, I mean, if you just show MNIST CFAR10 and then like, what's the usefulness of that? So in this case, we also can do something on data set for self-driving car. It's Udacity, and the architecture has been released from NVIDIA. We trained it. It has more than 1,000K neurons, and the input size is more than MNIST and CFAR10. 3 times 66 times 200, so that's like 39,600 input pixels. And we consider L infinity ball around these examples. So what we say, I have this scene of the road, and then I can change the pixel intensity of each pixel independently, and I want to see what is the steering angle predicted by the classifier. So here, the green line, if you can see, is the steering angle, which is the target, ground truth. And the blue one is the one that is predicted by the classifier, so it's quite accurate, close to the ground truth. Now, what we do is we try to compute certified bounds. How much can the steering angle predicted by the classifier can vary if I were to change the pixel intensity. This model is useful because if you're using self-driving car, your camera is going to capture different images depending upon the weather is sunny or cloudy or whatever, right? So you may want to say what is the range of angles that we can get in terms of steering. If this is going to lead me to a down the hill, or it's going to keep me safe, right? So yeah.
So the input of this is just some pixels of some image.
Yeah.
And the outputs of this network are steering and throttle commands.
It's the angle predicted by like how much should be steering angle, right?
Just
Steering angle.
steering. Okay, so it's like a end-to-end sort of So, have you looked at this for detection at all? Like actual perceiving objects?
Not yet. But there are works that actually do for different kind of threat models that they do verification of object detection as well. So
As far as this perturbation, how realistic is that in terms of pixel intensity? Like you said, we want to perceive something.
yeah,
Blah, blah, blah.
yeah.
I don't know if this has to look at
Yeah, so what you don't want is to big also like very large epsilon, because then it does not make any sense to verify garbage images. It's a very important question and a very central question. In the community, we have established certain values which we expect do not change the image too much. But I mean, it's very like hard. I mean, to define perturbation model, when I presented the deep poly paper 3 years ago, the question I got was that if I rotate the image of 8 by 90 degree, should it be classified as infinity? So when you even like consider this kind of perturbation, you have to look at the semantics of the object, right? So rotating the image of a waterfall by 90 degree may be not as useful as rotating some other object by 90 degree. So this is a very central problem, how to come up with specifications. Now, in the case of images and NLP, I would say that we have an easier time because we know what is correct, right? Now, if I give you a random data where like there are features that have values, how are you going to select the precondition? I mean, that is also the case in the case when you try to verify programs. What should make sense, and that actually requires a lot of domain insights. One thing that could be done is to somehow make a generative model out of your data set of the valid points that are possible, right? To actually somehow derive these perturbation models. People have looked somewhat into this, but it's not that easy, because in many cases, when it's like a non-image, non-NLP data, you don't even know what data point should exist in the domain or not. So people, when they design in robotics or other things like simulators, right, there is no notion of knowing if the data generated by simulator and you are training with the simulator, does it even make sense, right? Is that a real data or not? Because we don't know the distribution of the real data. So that's a central problem, how to actually automatically derive specifications. In this case, 2 by 255 is one of the standard values that people use, and that's what we have tried to verify. So here, the red are the ones that you would get if you were to sample from the L infinity regions, the different steering angles you can get. So here we use a custom sampling strategy based on PGD, which is a standard method. And the certified bounds are shaded blue. So when the image is a bit bright, and the certified bounds are tighter than if it is not. Okay, so we can also look at beyond L infinity geometric transformations. So here we rotate the image between -10 to +10. The challenge here is that in the case of L infinity, you can easily define your input region as a box region, and you can encode it as a MILP instance. You cannot do complete verification in the case of rotations, because the rotation transformation introduces a set, input set precondition. It's non-linear and non-convex. So the central challenge here is to approximate. What we do is we approximate this non-linear and non-convex set with a convex set. And I will not go into the details, but it uses some Lipschitz optimization and sampling. And we analyze this over approximate precondition with GPU poly. And if it can prove the property, then the probability also holds on the smaller set. In terms of results, here I show a CFAR10 network with 45,000 neurons and 4 layers. We can handle arbitrary combination of geometric transformations. So you can do rotation, sharing, scaling, translation, or brightness changes, and arbitrary combination of these. The first row shows a rotation between -10 to +10. And here we compare two methods. In the first method, the approximation of precondition is based on box. And in the second case, we generate a deep poly approximation of the precondition. And then the whole thing is analyzed with GPU poly. So there is a decoupling between what you use for neural network verification and how do you approximate the convex region for the geometric transformation. So in general, deep poly is a very general verification technique. If you come across some verification property that cannot be exactly encoded with deep poly, you can always approximate it with deep poly and then use the same techniques for neural network verification. What you see here is that the choice of approximation does make a big difference. So here I compare the precision of box precondition versus the deep poly precondition, there is a big difference in the number of images that can be verified, even though the network verifier is the same. So here the precision is 28, and here it's 87%. And the middle row is like rotation by ±2 and shearing ±2. The difference is 0 to 55%. We can also scale to more networks. We can handle 250,000 neurons in 9 minutes, and ResNet 18 with 500,000 neurons in half an hour. Somewhat scalable, but not the best. So you can also do more expressive properties, and there's another paper in the same session on 20th January. ReLU 1 is the robustness of the network is also correlated with the Lipschitz constant. How many people know Lipschitz constant here? Okay, they are, yeah. So the Lipschitz constant kind of measures how much does the network change within some region, and it can give you some idea about the kind of changes you can expect in the network output in a region. So the key contribution here is to compute this Lipschitz constant for combinations of non-differentiable transformations, like the rotation is non-differentiable. How to compute Lipschitz constant? We have a custom abstract domain. It's called DeepZ, and it computes this Lipschitz constant based on a notion of Clark-Jacobian, which is a classical concept from 1970s or 80s. And in this paper, we show how you can actually compute a static analysis for computing this Clark-Jacobian in a region. And here we can, I just show some results in terms of like what perturbation seasons you consider. So the transformations here are more expressive than L infinity. So here we consider some transformations based on contrast, age, rotation, some combination of this. We compare the Lipschitz constant computed by prior method with the one computed by DeepZ, and what you see is that it is always more precise and by some orders of magnitude as well. You can also do beyond images. So here I gave results for audio certification. So we are the first one to actually do any kind of verification for audio classifiers. So the main challenge here is that before the input is passed to the neural network, there are some custom nonlinear transformations applied to the signal before it can be processed by the classifier. So the kind of nonlinear transformations we are looking at is like log x, x square, and so on. And the network itself is an LSTM network. So we have different kind of nonlinearities like sigmoid x and tan h together. So what we do is we compute deep poly approximations and then use the same back substitution algorithm. Now, the open problem here is that how can we keep up with the creativity of deep learning designers? So if they come up with a new activations, how can I automatically create an approximation for that activation? Currently, what we do is not very scalable because you have to spend some time in designing and implementing these approximations by hand and also tuning them such that it's scalable and so on. Ideally, what you would like is to be able to at least generate some kind of approximation for any activations for a given class of functions automatically. Scalability, here we have an LSTM with 100 neurons on a free spoken digit data set. So here the recordings are utterance of digits 1, 2, 3, 4, 5, 6. And we want to prove that if we perturb by adding some noise to the audio signal, it is still classified as the same as before. So for small perturbation here, it takes us 8 minutes. We can also handle a GSC data set, which has more frames within 13 minutes or so. And as I mentioned, that you can actually, and what Matthew also showed was that you can actually use this kind of abstract interpretation based methods for training the network. So what you do is you have the standard verification loss, training loss, and then you add a verification loss, which means that you take the network phi, you take the precondition phi, you compute your approximation g of phi, and then in that g of phi, you find a point where the verification loss, which in this case for robustness is the difference of the logits, and then you add it to the normal training loss, and then you back propagate to update the gradients again. Now, this can be seen as like combining some kind of logical specifications with standard training. So we have like these methods for L infinity robustness and so on. The question is how to do it for general properties, how to define this loss function in a general manner. If I want to impose any logical property, the network can be trained such that it is easy to verify. As Matthew mentioned, the best network for CFAR10 with 2x255 is actually obtained by training the network with zonotope approximation and verifying with zonotope combined with mixed integer linear programming. Now, what you see is that 78% accuracy and 60% robustness. If anybody can at least come up with 80% robustness and 90% accuracy, that would be a milestone for the community. People have been trying it, but since the last 2 years, I have not seen this bounce being beaten. Okay, so Matthew showed like these kind of dimensions. I would just add 2 more dimensions, which was training. How can you actually design custom verification methods that are specialized for training? I showed some approximations that are specialized for verification, but maybe you can design relaxations that are very good for training particular logical properties. And then you can also look into designing custom training procedures. Maybe one of the reasons we are actually not able to get robust and certified robust and accurate network, it might be that it's just not possible to do it with standard stochastic gradient descent. So maybe we need to design more expressive optimization algorithms, right? Now, you can also use this kind of formal methods for explanations, generating robust explanations. Usually at the moment, I don't like this approach in the sense that if I want to generate explanation, somebody just gives me a saliency maps and then he says, oh, look, it corresponds to human intuition. Like that kind of explanation, in my view, lacks faithfulness. It only gives explanation for a single point. There is no guarantee if it describes the more general behavior. Now, if you give that kind of explanations to somebody who trusts them with a blind eye, they might be misled into thinking that the network behaves in a way that they expect, while it might not be. So you can actually use some of these methods or design new methods to generate explanations which are guaranteed to hold, in the sense that they exactly describe the network behavior in some region, right? So this explanation is faithful while also being understandable. Of course, I can generate some explanation which is like a polyhedral formula with 7,000 variables. Nobody will understand it. So what I want is some robust explanations that are easier to understand, but are also formally verified to be faithful. Now, much of the work is also depending upon generating linear first order approximation of the neural network behavior in some region. Can you actually do like better in terms of generating second order explanations, which also take into account the interactions between the different neurons or different perturbations? So in terms of open problems, what you want and what we have been envisaging is what Matthew showed is, I think if we are going for real world adoption of any of these machine learning systems, you need to have some kind of guarantees. I agree that we cannot provide the absolute guarantees that we usually get, or let's say more guarantees that we get when we try to verify programs. So if I prove in the case of programs that the bubble sort algorithm is sorting the array correctly, then it holds for all the inputs in the universe you can come up with, right? In our case, we don't give guarantees for all the inputs in the universe, but for a subset of the universe. I would like to argue that this is still better than just reporting standard test set accuracy, which just reports the network behavior on a finite set of inputs. So this kind of approaches has some value, but of course not the absolute values you would like. So what we would like is that when somebody in the future wants to deploy any of these neural networks in the real world, can they provide guarantees about behavior? Can they say something about how the network behaves, explanations, and also guarantees on robustness and fairness and so on? So there's a lot of work on like verifying vision and NLP models, but there are neural networks that are for other domains as well. So one thing what we want is that we do all these kind of things, but the system that we actually develop for verification, they should be accessible to a general audience like PyTorch and TensorFlow are, right? So there's no point of developing things that are only tailored for MNIST or CFAR10. We want that anybody who uses deep learning should be able to benefit from verification, right? So there is one thing about like the methods that we develop, deep poly can work, but if the implementation itself is only going to work on some fully connected MNIST CFAR10 network, practically that's not very useful. So can we actually develop some framework like PyTorch TensorFlow that is very easy for anybody to use, not only somebody that has a computer science knowledge, but there are other users of deep learning like chemistry somewhat, right? So building those tools is very important than just getting into the race of like verifying more and more with custom properties. So another thing that I have actually talked when I talk with industry people is they are interested in is when a network fails, can you tell me reliably why does it fail and give a understandable explanation. So maybe you want to say that, oh, my network only fails when I apply this perturbation, let's say -5 to +5 rotation, right? So that kind of explanations people want when they want to see that the network does not verify something that you want it to verify. So just verifying itself may not be enough. You want to provide locations or causes of failure. Then you may also, once you have located the causes of failure, you may want to repair the network incrementally. You don't want to retrain the network from scratch again because sometimes you don't have access to the training data or it's just too expensive. So there you want to repair the network so that the new behavior are taken into account while not forgetting what you had learned before. As I mentioned, one more property you want is that can you automatically generate specifications from the training data? And that has very much relevance for non-NLP and vision domains. And can you actually verify more expressive specifications? So L infinity or geometric specifications are just defined over the inputs and outputs of the network, but you can also define specifications on the first order property or second order property of the network, like defined on gradients or something else. You can also define temporal properties like if I have a neural network in a reinforcement learning controller, the controller makes decision that does not break the system and so on. One more thing is proof, transfer, and repair. So this question gets asked many times to me. If I train a network, I spend 1 day verifying it on 10,000 images. Now, if I change the network slightly, maybe fine tune it, or I apply some adversarial training, and I get a network that is very similar to the one previously I had, do I need to spend 1 more day again to train this network, to prove this network? So the question is, can you use some of the proofs that you had done for the first network for speeding up the proof for the second network? Of course, the grand problem is that we actually cannot prove any L infinity specifications for ImageNet. We have been able, or other researchers in the community have been able to prove weaker specifications like robustness against patches and so on, but L infinity robustness for ImageNet, nothing exists. Of course, you want to train accurate and certifiably robust networks. And there's also work on actually verifying correctness of ML or PyTorch code, because even the standard semantics of these languages are not defined. So there are works on actually defining the semantics of these languages and then proving some correctness properties based on those semantics. So one of the conjectures here is that the reason why we cannot get robust and accurate network is maybe the ML code or the PyTorch or TensorFlow are doing something wrong during optimizations and so on. So with that, I would like to conclude, and I would leave you with the 4 most important slides from this presentation, and also the future challenge, which is to get cyber physical systems that can have formal guarantees. And I'm open to questions.
Sorry. Yeah, I was wondering, I didn't see on your open problem slide certificates for verification. Is that because it's solved, or is that? So if, I mean, a proof of why it's, so some SMT solvers can spit out certificates, so they can prove your property holds.
Mhm.
They can spit out a proof of why your property holds that is polynomially efficient to check. I mean, it's much harder to come up with that proof in the first place, but you can, given the proof, it
Yeah.
gives you a step-by-step procedure for proving why your property holds.
Yeah.
Do any verifiers, does Aaron spit out certificates, or would it be possible to?
Yeah, you can actually, yeah, you can configure the Iran to spit out the certificates.
You can?
Yeah.
Okay, so using the certificate, you can replay the proof to.
Yeah, we actually have a recent work. What we do is that we have 2 networks if they are similar to each other, right? So maybe one is a normal network, and then you do some pruning or you do some quantization. Yeah. So what we can do is we can get the proof for the original network and try to transfer it to the second network and see whether that proof works on the second network or not. What we have found is that this proof usually holds.
Okay, cool. I guess so. The certificate is actually the bounds at each node or each layer, or.
So usually, what happens is that overall, what is happening when the neural network does classification? It takes a point in high dimensional space and maps it to the output class. So with each transformation in the layer, the points that are maybe farther away in the input layer are getting close together, right? So this kind of proof transfer you cannot do at the first few layers, because there, even if you start with properties that are very far apart, they remain very far apart in the first few layers. But if you go in middle layers, as you go deeper in the network, the proofs become similar, and then you can exploit that to do this kind of proof transfer.
Okay, cool. Thank you.
Any?
I have a related question on proof transfers. So do you think you can use proof transfer to train robust networks? For example, at each step of the training, you have a robust network and you also have a proof. And whenever you perform a gradient step, you verify that, it stays the same. So have you thought about this, or is this idea worth exploring?
Yeah, we have not thought about it or not done it, but I guess something like that can be done. You may want to actually learn maybe universal representation at an intermediate layer that you can use during training. So you can say that, hey, if my intermediate representation is like this, then I don't need to check whatever will happen later in the layer, or I can just keep it as a database and say that whenever I'm training a new network, the intermediate representation has to look like this. But not much has been done. Proof transfer, recently only people have been looking into it, but not much work. One more thing where you can do proof transfer is when you do temporal specifications. So across the steps, there can be a lot of commonalities in the proof when you go from one step to the next step.
Thanks.
More questions? Well, I think there's already many questions asked and answered during the talk.
Okay.
So
There's nothing on air meet? Okay, that's good.